Okay, I guess it's on. Okay, so it's my pleasure to introduce Yael Niv, who is our invited speaker of the morning. So Yael Niv is an associate professor at the Neuroscience Institute and in the Psychology Department of Princeton University. She's done amazing work in computational neuroscience, in particular on the understanding of the neural basis of reinforcement learning and decision making. She has an awesome op-ed that came out a couple of days ago that you should all read about how policy should be set based on data on human decision making instead of economic theory. Yael's won many different awards, including a PCASE award and a NIPS Outstanding Paper Award. She did her PhD work at Hebrew University in the Gatsby Computational Neuroscience Unit, which is where we first met. Over the years that I've known Yael, she's been a huge supporter of the advancement of women in the field. So, for example, she started a website called Bias Watch Neuro that tracks the gender ratio of invited speakers at neuroscience conferences, which is awesome. And today she's going to be telling us about learning state representations. Thanks.
Thank you so much, Catherine, for that wonderful introduction. And it's a great honor to be speaking here. So my lab studies learning and decision making, which when you think about learning and decision making, some of you might think about an artificial intelligence learning to solve a complex sequential actions game. Or maybe even something more complex, like a task that involves strategic decision making with an enormous number of states. But these are tasks that arguably people are not very good at solving. So instead, when I think of artificial intelligence coming from psychology and neuroscience, I think of something, a program, an algorithm that can perform a simple task that we perform on a daily basis, like, for instance, crossing the street. So how do people solve this mundane task? It might seem mundane, but it's actually complex because the environment is so cluttered with information. So the question that I ask is, what information do we represent in order to make a decision in this situation? Is it the shops across the street or the colors of the cars? Obviously not. So we've learned from our life experience that the features of the environment that are relevant to this particular task are, for instance, the time left on that pedestrian light and the speed and the distance of approaching cars. So we can ignore most of the scene and represent the complex multidimensional task as a much simpler one. And that's kind of a theme through my talk today. So I'm talking about a task representation, and I'm saying task-specific representation because if we were standing at that same street corner and hailing a taxi, of course our representation would be different. Now we would ignore the pedestrian light and instead represent the colors of the cars in our decision-making apparatus, whatever it is in our brain. So ignoring irrelevant parts of the environment is especially important for learning and for reinforcement learning. So imagine if I start crossing the street and a car honks at me. What do I learn from this? I wouldn't want to limit my learning only to this specific street with 6 people on the crosswalk and a white bus pulled over. That would be idiotic, basically. So I would clearly want to generalize to other street crossings. So the fact that I'm representing only some parts of the environment allows me automatically to generalize across all the things that I'm not representing. So the question my lab has been asking in the last 10 years is, how do we learn efficiently from relatively little experience for each task a representation of the environment that supports correct decisions and also allows proper generalization of learning? So to people who think more about AI, you would know that this is a problem that any AI in the wild also encounters. So for instance, self-driving cars analyze only the parts of the environment that are relevant for success, and the rest is completely ignored. But in this case, deciding what part is relevant and what is not is usually done top-down, hand-coded by experts. For instance, the self-driving cars that I know from Mobileye see the world in monochrome. But in real life, we have to learn this reduced representation of the environment for each specific task, not only for driving, from trial and error. So I want to be very clear about the computational problem that we have here, that our brain has. So in the field of reinforcement learning, there's a concept called the curse of dimensionality. the more dimensions the environment has, the more states or combinations of features that we have to learn values and predictions for and policies for. And this makes learning prohibitively expensive in terms of time, in terms of the amount of experience that we need to accumulate to truly master the task. But as you know, because you've crossed streets and gotten here alive, it only takes several trials to learn how to cross a street. And this suggests that the brain performs some drastic dimensionality reduction, and it performs it very automatically. But it's not even as simple, and I'm saying simple in quotes because that alone is hard, as reducing the dimensions of the observable scene. Sometimes it turns out that the most important parts of the task state are unobserved. So imagine shortly after you move to New York, you see this. So now the light is saying stop, but someone is crossing the street. It doesn't even look like they're in a hurry. So you start learning that even on wide 4-lane streets, people can jaywalk without worrying. So you might start to learn a new behavioral policy, that you can jaywalk rather than use the light. But here it's really important that you don't generalize too widely, because it turns out that in Washington, D.C., if you do the same thing, you will get a ticket. So the point is, although the streets and cars and shops look relatively similar in both cities, they all have Starbucks. You should separately represent and learn about street crossings in New York and street crossings in D.C. as two different states. So what I'm saying is that all of learning basically is about generalization. No two instances of experience are ever exactly alike, so we have to use the statistics of the task to infer when two seemingly similar situations are really the same thing, so we can learn from one situation about the other, and when they are not. So the way I'm going to think of task states and how we learn task states today is as clusters of events or observations that are deemed similar enough to allow generalization across them. And a good computational model for this kind of parsing of the world into clusters is Bayesian inference with an infinite capacity prior. So this is also called a Chinese restaurant process prior, and many of you will be familiar with this. So this is a generative model of the environment, and the idea is that the observed events, for instance, a pedestrian on the street with a red light and no one honking, are caused by latent causes. For instance, the fact that you're in New York. And in particular, the prior assumption is that there are few latent causes that cause most of our observations. That is, a latent cause that has so far been prolific and caused a lot of observations is, all else equal, likely to cause the next observation. But that having been said, we don't want to limit ourselves and assume a bounded number of causes, so the possible number is infinite, and that's why it's called an infinite capacity prior. So mathematically, this can be expressed by this simple equation, which is the only equation you'll see from me today. So the probability of the latent cause at time t being from cluster being k is proportional to the number of events already seen, or the number of observations already seen from that cluster, and there is some small probability alpha that's a parameter of the prior here for starting a new latent cause. And finally, to do inference in this kind of model, so to infer the generative structure from observations, we assume that each latent cause has characteristic emission probabilities, so it tends to produce similar observations. So this is the model that's going to guide our thinking. And first I want to convince you that humans, not AIs, perform this kind of inference. And so our main hypothesis here is that people group experiences based on similarity. So they take similar experiences, assign them to the same latent cause, which is basically the same state, and generalize learning across them. So to test this, Sam Gershman, who was then a graduate student in my lab and is now faculty at Harvard, presented human subjects with a task like this. So they saw circles on the screen, and we asked them to say quickly how many circles they saw. So they had to type a double-digit number within 2 seconds. And so they type the number, and then we show them the true number of circles. In this case, there were 39 circles. And so here's another trial as an example. So we weren't interested at all in their ability to count quickly, but what we wanted to see is how they learned from feedback from the true number of circles to approximate the number of circles on the next trial. And that's why we made them guess very quickly. And the important structure in this task was that the trials came in two different flavors. So as you saw, sometimes all the circles were red, and sometimes all of them were yellow. We didn't say to the subjects anything about color, but actually color was important because it did determine the average number of circles on each trial. So in fact, there were two conditions, or two blocks in the task, which a participant performed many of each kind of block intermingled. In both of these blocks, there was one color that I'll call yellow, although it was a different color in each block, where the trials, the number of circles in those trials was on average 65. And then the other color, which I'll call red, but it was a different one in each one, had, I'll call that the alternative mean. So the alternative mean on one condition was 35. So now we have 65 yellow, 35 red. And in the second condition, in different blocks, the alternative color was mean 55. The yellow was always 65. So our hypothesis was that because of the similar statistics, in condition 2 here, the 55-65 condition, our human participants would basically ignore color, and they would learn the overall mean, which is 60. So when we ask them to guess on the yellow trials, they should guess something close to 60. Whereas in the first condition, the 35-65 one, because the two trial types are sufficiently different, subjects would separate learning according to color. So they would basically encode color in their state representation and learn two separate means. So when we ask them about the yellow color circles, they should be more accurate and closer to 65. And this is indeed what we found and what we've seen repeatedly in several experiments since then. So in condition 1, they're guessing closer to 65. In condition 2, they're guessing closer to 60. And the difference there is significant. So what I'm saying is that inference about latent causes determines the boundaries of generalization, this super, super simple task, the simplest we can think of. And it suggests to us that subjects are automatically and implicitly, without being aware of it necessarily, inferring whether all the trials are due to one distribution, so one latent cause, and then they're averaging over all that experience, or two distributions, or two latent causes are in play, and then they're learning separately about the two colors. And so this inference is determining their generalization. In machine learning or reinforcement learning, we would basically call these latent causes the states of the task, the entities for which you need to learn a prediction or a policy. So what I'm doing is I'm casting real-world learning as clustering with an ever-growing set of clusters. And in particular, if you think of how we, you and me, learn as our daily life, I'm suggesting that as we go about our business in the real world, bits of experience impinge on us all the time. And we have basically no choice, if we want to learn, than to cluster these experiences into states based on similarity, so that learning can happen across, sorry, what happened here? A mess. So that learning can happen across, so learning can happen within these cluster boundaries and not across them. So more than that, I'm going to argue that this inferred structure of the world is also how humans organize our internal representations of the environment. So basically, how we store events in memory. And this is reminiscent of what deep neural networks do and how they represent and store at the same time internal information. So to test this, this was a learning task, not a memory task. To test this, we want to do a similar thing in a learning scenario. So what we did, and this is, again, Sam Gershman together with Angela Radulescu, who was a research assistant then and is now a graduate student in my lab. So they ran this experiment, again, on people. So they asked people to memorize little line segments. And so to coax undergraduate study participants who are not super interested in our study to pay attention, we asked them first to try to predict the line. So here it says, please predict the next line. They draw it with a mouse, and then we would show them the correct line. We were really interested in the correct line. We gave them some points that reflected how close their prediction was to keep them engaged. And then here's another trial, predict the next line. They draw it, they get the true line. And if you notice on the bottom, there's this red circle that tracks what trial they're in the block. So that's moving right on each trial. And at the end of a block of trials, so let's get to the last trial. So this is the last trial of the block. So please predict the next line. Here's the next line. Right at the end of the block, we ask them to now try to recreate from their memory one of the segments from one of the very first trials. So what's going on behind the scenes here? So what I'm showing you here is for every trial in the block, which is one circle in this graph, the length of the line on the x-axis and the orientation of the line on the y-axis. So you can see that on every trial, the length and orientation change very gradually, very slowly. And it's kind of a random walk with no returns. But like in the circles task here, too, we had two types of blocks that the same person completed. Some blocks were like this one. They're the gradual blocks. And other blocks looked like this. It's very similar, except in the very middle of the block, there is one change that's 4 times as big as normal in both the length and the orientation. And so we call these jump blocks. And similarly to before, our hypothesis was that in the gradual condition, because all the events, all the stimuli are very similar, they would all be grouped together into one latent cause and also stored together in memory. So basically, every little line segment would interfere with all the others in memory. Whereas in the jump condition, we expected to have 2 different memory traces, one for the lines before the jump and another for the lines after the jump. And indeed, if we run a computational model of clustering, in this case it's a Dirichlet process Kalman filter, which is an extension of the Chinese restaurant process that I showed before, then it assigns the jump condition into almost 2 latent causes, whereas the gradual condition is closer to 1 latent cause. So we test this by asking subjects to recreate from memory that trial from the very beginning. So what they're doing is they're drawing some line on the screen. So I've marked that with an X with some length and some orientation. And what we want is for that line to be very close to the first or second, whatever we ask them about, lines in the block. So we can measure the Euclidean distance between what they recreated and the first line, and also the end of the block. And what we want is a short distance to the beginning of the block and a long distance to the end of the block, so less interference from the end of the block in their memory. And indeed, what we get is that they are better at reconstructing in the jump condition. So the distance from the start is smaller in the jump condition, and the distance from the end is larger, showing that they are basically more accurate. So what I'm saying is we infer context or hidden causes to generate a representation of the states in the world. And what I want to ask now is, can we read out these inferred representations from the brain? So far I've shown you psychology, but now comes the neuroscience. And so the reason we might want to do this and read out these representations from the brain is that instead of using artificial intelligence to solve tasks that people are bad at, like chess or Go, I personally would like to see an AI that is more like human intelligence. That is, it learns to solve many tasks with little data for each task. And my argument is that the way the brain does this is by taking complex tasks like crossing the street with a whole variety of sensory input around and casting them into a simpler task, like, I'm in New York City and the pedestrian light just turned red, should I cross or not? And so the idea is if we understand how the brain makes this transformation, so what information it uses to inform the state and how the state changes through the process of learning, how we learn to create a state representation for a new task, then maybe we can get inspiration for solutions for this problem in AI. So where in the brain can we read out these representations? And this brings me to the mysterious orbitofrontal cortex. The orbitofrontal cortex is an area above your eyes, kind of right in the front and really above the orbits. And it's considered kind of the frontal cortex of the frontal cortex. So the frontal cortex in neuroscience is the whole front of our brain is the area that's more involved in high-level abstract cognitive functions. And the frontal cortex of the frontal cortex is implicated in the most abstract cognitive functions. And indeed, this area has really vexed researchers for the last 20 years because it's not really clear what it does. What we know from decades of research is that the orbitofrontal cortex has a pervasive role in decision-making in the lab. But this is a subtle role. So you can hurt your orbitofrontal cortex pretty easily. It unfortunately sits atop a ridge in the skull. That means that even minor car accidents can cause orbitofrontal damage. And what we know is that people who have orbitofrontal damage are impaired in decision-making in a bunch of tasks. But there's basically almost nothing that they totally can't do. So without your orbitofrontal cortex, you could basically live a normal life. But in some way, it's involved in kind of your decision-making personality, like making good life choices, abstract big choices in the real world. And in a famous case here is a patient called Elliot, who was studied by Antonio Damasio, who, after suffering damage to his orbitofrontal cortex, divorced his wife, quit his job, and married a prostitute. But this whole time, he performed well in laboratory tests of intelligence, reading comprehension, visuospatial abilities, facial recognition, any of the classic battery of tests. So what is going on here? So skipping all the gory neuroscience details, I'll cut right to the chase and tell you that based on results from recordings in animals in the orbitofrontal cortex carried out by our collaborators Yuji Takahashi and Jeff Schoenbaum at the National Institute on Drug Abuse, we hypothesized that it is the orbitofrontal cortex that encodes the current state of the task. That's its abstract function. And in particular, and this is based on the patterns of deficit, the specific patterns of deficits that happen when the orbitofrontal cortex is damaged, we hypothesized that this role of the orbitofrontal cortex is especially critical for what we call inferred states, or these latent causes I've been talking about, or in reinforcement learning speak, partially observable states, like in POMDPs. So we put forth this hypothesis based on previous data, but now, of course, like any other of our computational hypotheses, we have to test it and see that it really does hold water. And so 2 postdocs in my lab, Nico Schuck, who just recently started a lab at Max Planck Berlin, and by the way is looking for postdocs, and Mingbo Kai, who's here at NIPS and presenting a poster in the workshops, devised this task that we thought would have to rely on representations of partially observable states. So here's the task. So participants, again, human participants, see stimuli that comprise of a house overlaid with a face. And they have to judge whether the face is of a young or old person, or whether the house is young, that is modern, or old, old-fashioned. And they have to judge only one of these 2 categories, either faces or houses. And the way it works is we start by telling them what category to start judging. And we give them a rule. We tell them that whenever the age in that category switches, for instance, from old to young, then they need to switch category on the next trial. So this might be a little bit confusing, so let me demonstrate it with a couple of trials. So here's the beginning. A new block begins. You'll start with faces. Good luck. So here's our first face, and it is a young person, so they press the button for young. The second face, also a young person, so we're staying in faces. But now we have an old person, and the rule is when the age switches, now you change categories. So on the next trial, we are going to judge houses. And this is a modern house. Oops, sorry. And on the next trial, this is an old house, so now we're going to switch back to faces. So this is how the task works. So before we move on, I want you to contemplate for a second about this task and whether you think if I gave you a computer now, you could perform it above chance. And I bet you could. I bet anybody in this room could do that. And so I want you to contemplate for a second something that I can't explain yet with all the data that we have, which is what just happened in your brain. So how did you create, from scratch, in mere seconds, a representation of this task that I totally made up out of thin air to the point that you can now perform it? And this is, another challenge, this compositional creation of states for AI. So what are the states in this task? So first of all, I should say that we trained subjects for about an hour, so they did 600 trials of this task, and they got really good. They start really good, but they get even better, so they can perform the task with extremely low error rates, so below 2.5% errors. So they're performing whole stretches of trials without any error. And this is great. That's what we wanted. This is not a learning task at this point. It's fully instructed because we knew that once they're performing the task at that level, they have to be representing in their brain a lot of information. Basically, they have to represent a state that comprises of 4 parts. One part is the category of the current trial. So are they judging faces or houses? So there are 2 options there. The second part is what is the age of this current face or house on this trial, so old or young. So there are 2 options there as well. But they also have to represent, and both of these options, they're on the screen, but they have to be, whether it's faces or houses, has to be internally represented in the brain because that's not given by the stimulus. And they have to also represent the age of the previous trial that I'm marking here in parentheses. So everything in parentheses is the previous trial, because they're going to have to compare the age in the previous trial to the age in this trial to decide whether they change categories on the next trial. And finally, they have to represent the category on the previous trial, because if they just switched categories, they don't have to compare ages, because the comparison is only within category. So because each of these different state features has 2 possibility, face or house or young or old, there are basically 16 states in this task. So the Markov states, the states that have the information for performing the task correctly, which the subjects are doing, there are 16 different options here. So our main question is, can the current state be decoded from the orbitofrontal cortex? So does the orbitofrontal cortex represent the current state of the task at each point in time? And to test this, we used a technique called multivoxel pattern analysis. So first, we had subjects perform this task in an MRI scanner, so we can measure their brain activity on each trial of the task. And then we looked at all the activity in the orbitofrontal cortex, so it's illustrated here with these grayscale squares. So we looked at all the voxels, the 3D pixels in the orbitofrontal cortex, and we know on each trial what the true state is, so we have a bunch of labeled data, basically. We have the brain activity on all of the FY-FY states, all the FY-FO states, and so forth. And so we can take these and train a support vector machine classifier to classify, based on brain activity, what state the subject is in each trial at a time. And we can do this, so we had 5 different blocks of trials in the task. We can do this, we can train the classifier on data from 4 blocks, and then use it to try to classify the last block. And we do this, leave 1 block out for each block. And what you can see here is that, yes, we can, significantly above chance, classify from this from the activity in the orbitofrontal cortex what state the subject is in each trial. So there are 16 states, so chance is 6.25, and our performance is at about 12%, which is significantly above chance. It's not super high, and there are many reasons for that. One is that the orbitofrontal cortex is notoriously difficult to record signals from with fMRI because it's right above our sinuses. It's located in a bad place for many reasons, but that's where nature put it. So, okay, but also, so we have 16 states, and we can look more deeply. So imagine the state is FYFY, and our classifier said FYFO. So this would be considered wrong classification. We would put that in the almost 88% wrong trials. But the classifier was right on 3 of the 4 components. So we could look for each state, the same 16-way classifier, what components is it correct on? And what we see here is that we could classify significantly above chance with this 16-way classifier the category on the current trial, the category on the previous trial, the age in the previous trial, so all these unobservable things. The only feature that we couldn't classify with our classifier above chance, and we've replicated this since in another experiment, is the current age. And arguably, that's the only one that's observable given all the others. Or there are also other reasons why we might not be classifying this component. It might be because this is really an action and not part of the state. But it seems like really all the necessary parts of the hidden state are there in the orbitofrontal cortex. So this was our a priori hypothesis, and hooray, we got it right. Doesn't happen often. And one thing we can ask is this a unique function to the orbitofrontal cortex? Maybe state representations are so important that they're represented all over the brain. So what we can do here is take a spherical searchlight throughout the brain and ask in which areas of the brain can we correctly classify these 3 hidden components above chance. And here, to our actual real astonishment, we found that the orbitofrontal cortex is the only area in the whole brain that includes all of the necessary information for the task. And I don't have it in my slides here, but we also looked for information that was not necessary for the task. So is this state representation really the minimal it can be? And also, the orbitofrontal cortex doesn't have any unnecessary information. Other brain areas have unnecessary information, are missing some of the necessary information, don't really look like the state representation that we're looking for. So finally, the degree to which we could read out the current state from the orbitofrontal cortex turned out to be related to performance on this task. So although subjects had a low error rate in general, we found that across subjects in which we had higher classification accuracy, so it seems like the orbitofrontal representations are better delineated, are also those who had fewer behavioral errors. And so this suggested to us that these representations are really important for performance of the task. And we could look more directly, specifically at the error trials, which we had discarded from all the previous analyses, the training of the classifier and the testing of the classifier. And what we see here is that these error trials, so I'm marking here, the error trial is at time 0. It's this shaded, and it's the empty circle. So on these error trials, whereas normally we can classify the current state well above chance, we can see the control trials here, the non-error trials are in filled circles. Those are significantly above chance. On the error trials, classification accuracy dips below chance. So again, this suggests that a representation of the incorrect state in the orbitofrontal cortex led to the behavioral error. Okay, so basically behind the scenes, if you were writing down the Markov model of this task, a Markov state representation, this task I could explain to you in a few sentences and that your orbitofrontal cortex could create a representation for on the fly basically consists of this cognitive map of states and their transitions. And essentially, what I'm saying is that the orbitofrontal cortex, which, by the way, is an area that's especially well developed in humans compared to animals, even to non-human primates, to monkeys. So this area, according to our findings, is what allows us to learn and solve complex tasks that involve partially observable information. And maybe in a sense, these representations and this brain area that stores the representations is what allows us to be basically as intelligent as we human intelligences are. And one important open question that I already mentioned and that I don't have an answer to yet, and we're working on this now, is investigating how this flexible representation is created on the fly. Okay. So to summarize what I've told you so far, I suggested that as bits of experience impinge on us in our daily interactions with the world, we cluster these experiences together into task states based on similarity. And I suggested that the orbitofrontal cortex represents the current state of the task, so the cluster of experiences that are equivalent for the purposes of the task. And importantly, that learning happens within a cluster, so these clusters are effectively task states, not across cluster borders. And so the last question I want to ask is, can we use this understanding of representation learning in the brain to our advantage, not only for AI, but for controlling real learning in the world? And so here's a task where we badly want to influence learning. What you're seeing is a video of rats undergoing fear conditioning. So there's a light there. Oh, they got a shock. Did you see they jumped when they got a shock? So they heard a tone, and at the end of the tone, they got a shock. And now, 24 hours later, we can test what happens when they hear that tone again. When the light in the middle will turn on, the tone will be on. We don't have sound here. So this is a classic fear response of rats. They are freezing. You can see that the timer is still moving on top. It's not the video frozen. This rat on the very bottom, against all odds, is trying to reach the food. Okay. So this is a classic fear response, and you can get this in rats after 1 or 2 pairings of a tone with a shock. And so now that the rats have learned to fear the tone, an important question that neuroscientists and psychologists have asked is whether we can undo this learning. And that's because this learning can be very maladaptive, for instance, in cases like post-traumatic stress disorders or phobia. So the idea is that there's a very strong traumatic memory or strong traumatically learned association here between the tone and the shock, and we want to undo that learning. So the most straightforward idea is to do what's called extinction, so to extinguish the link between the tone and the shock by presenting the tone many times without a shock. And indeed, we can do this until the rat stops freezing when the tone is on. But it turns out that this type of extinction is really not robust. And when we test the animals later, so we play the tone, let's say, a day later, it's very easy to reinvigorate the fear and see the rats freeze again. For instance, if we give a reminder shock, no tone, just a shock to the rats, and then play the tone, they freeze a lot more than if they didn't get the reminder shock. And the same thing happens if you just wait a long time before the test. If you just wait a month and then test them, the fear comes back spontaneously. So this suggests that in extinction, the animal is not really unlearning the prediction of the shock given the tone, as reinforcement learning would predict, but what the animal learned in the original traumatic memory remains intact but dormant. So extinction doesn't work, and the question is, why doesn't it work? And so my suggestion is that maybe we've been underestimating rats, and that we thought they were just learning to associate observable events, the tones and the shocks, whereas in fact animals might also be learning latent causes like humans. So when they see these 3 trials of tones and shock, they might put them in one latent cause, one cluster. And now when the first extinction trials arrives of a tone with no shock, there are 2 options. In reinforcement learning, we would say that now the animals are learning that the tone only predicts the shock with 75% probability, not 100%. So this is modifying an existing cluster. But I've suggested today that the rat might choose to do something else. Because these trials are not similar, the rat might do representation learning and basically create a new state for the task. And this means that it would protect the old learning from being modified. But we want to modify that old learning, right? We want to erase that traumatic memory. So how can we do that? So according to our model, similarity is key. So the question is, what if we make extinction more similar to acquisition? So this is what we did. So in training, in acquisition, we had 3 trials of a tone and a shock. And then in extinction, the next day, the first trial, there was a tone and a shock. And then the next trial, a tone with no shock. And then tone and shock, and 2 tones with no shock. And tone and shock, and 3 tones with no shock, etc. So we're basically gradually weaning the rat off the shocks, and we call this gradual extinction. And we compared this group of rats to a group of rats that underwent regular extinction, so no shocks in extinction, same number of trials. And also we compared to a group that we called gradual reverse, where we started with shocks but fairly spaced apart, and they became more frequent. So the idea was that in gradual extinction, because the trials are always similar, relatively similar to what happened before, they would all be clustered together, and we would manage to slowly dilute the probability of shock in that original cluster through those trials that are not that don't have a shock, whereas that wouldn't work in the other 2 conditions, because at the beginning of extinction, the other 2 conditions, in regular extinction, gradual reverse, a new cluster would be formed at the beginning of extinction. And so then we test for fear, either 1 day later with a reminder shock, or in another experiment 30 days later, so a month later, for spontaneous recovery. And it worked. So here I'm showing how much they're freezing on the test compared to the very end of extinction. And you see here that in standard extinction, both paradigms, freezing is a lot larger, or the animals freeze more in the test as compared to the end of training, whereas in our gradual extinction procedure, they're not freezing more. These are both not significantly different from 0. So to summarize, overall, the story that I've told you is what I call shallow learning with deep representations. So basically what I've argued is that the simple processes of reinforcement learning, like this rat learning to press a lever, learning to assign values and to derive behavioral policies for states of the world, can be so effective and efficient in real-life situations due to what Lisa Couture coined so aptly yesterday as the unreasonable effectiveness of structure. That is, what I'm saying is we can use this shallow learning, shallow reinforcement learning effectively because we have other sophisticated supportive learning functions that take our daily experiences in our cluttered, complex world and cluster them together into simpler representations, these task states that shape learning and decision making. And as neuroscientists, we know a lot about what brain areas are responsible for these different functions. I denoted a bunch of them here. We only talked about the orbitofrontal cortex today. But the point here is that because we know these brain areas, we can read out learning-related quantities like states and also others, values, prediction errors, and use these readouts to inform our understanding of the computational processes that the brain employs in learning. Which brings me back to the challenge that I had posed for AI. And I want to add to it here. So not only learn to solve many tasks with little data, but also flexibly recombine these representations on demand to solve more tasks. And in meeting these challenges in artificial intelligence, I believe that understanding how the brain does this can provide us clues. So with that, I want to express endless thanks to my fabulous lab, past and present. I had to Photoshop some people into this picture. They did all the work that I told you about, our many wonderful collaborators, and our generous funders. And I want to highlight 2 of my lab members who are here and presenting work at NIPS. So Jessia had a poster at the Women Machine Learning workshop on Tuesday, and Mingbo has a poster at the Big Neuro workshop on Saturday. And that is all. Thank you.
Awesome. So are there any questions for Yael?
Maybe sorry, is this on?
It's working.
Okay, yeah. Very quick question.
Sure.
How many human subjects participated in the trials, and how were they distributed on age groups, gender, etc.?
Oh, that's a good point. That's a good question. So how many humans? So in each of these experiments, it's a little bit different. About 30, 40. We've replicated all the results again and again. These are usually undergraduate subjects. We haven't tested children, for instance, for this process, and it might be slightly different in children. So there's evidence from rodents to suggest that children who don't have a very well-developed orbitofrontal cortex or hippocampus or other areas of their frontal cortex cluster more broadly, so they generalize more broadly. We also haven't looked at older adults in this task, so it really is kind of 20-year-olds.
Thank you.
Yeah.
Hi. I wonder if there's any possibility of distinguishing between two possible ways that this clustering might be done. One is a hard clustering, perhaps you might say greedy, and the other one is marginalizing over the clusterings, as you would normally do in a Chinese restaurant prior or something.
Yeah, that's a really great question. So I've told the story and I've drawn it here as if it's hard clustering, but in all our models it is soft clustering and approximating and basically marginalizing over the posterior. Whether humans do the marginalization or more of a maximum posteriori we have not. It's hard to test that because the differences are very subtle and it's very hard to see. But
rather small signal, haven't you, there, really?
Sorry?
You've got quite a small signal, sort of 50% or 54%.
Yes, I mean, all that I've shown you is basically the very kind of high-level conceptual predictions of the model, that all of the parameters, whether it's a Chinese restaurant processor, an Indian buffet processor, all of those don't really change our predictions at this course level.
How soon can you classify states from neural activity, and are some states earlier developed than others?
Yeah, that's exactly what we're working on now. So how soon can we really classify? Can we really read out in a task where we don't have ground truth what is the state in the orbitofrontal cortex? We're working on that. It will probably require to start with a simpler task that doesn't have 16 states. So we're working on a task that has fewer. I have high hopes. I have high hopes that we'll be able to classify not only a lot better, but also in real time. So we'll be able to give a subject feedback based on their representation, not based on their action, basically shape their representations. But it is a long-term project.
All right, thanks very much, Yael.
Thank you.